IB Physics M2025, Time Zone 2, SL Paper 1A, Question 5. A spring obeys Hooke's law and has a spring constant K. The spring is extended horizontally, and the extension of the spring is x. When released, the spring returns to its original length in time delta t. What is the average power developed by the spring as it is returning to its original length, or as it returns to its original length? Okay, so what is average power? Well, power is defined as the rate at which work is done. So average power is the work divided by the time elapsed. And work is energy transferred to or from an object by a force. So power is a measure of how quickly energy is transferred or transformed. So what is the energy that is being transferred in this problem as the spring returns to its original length? Well, add an extension of x before the spring is released. All of the energy is elastic potential energy. Once released, 100% of that elastic potential energy is converted into other forms of mechanical energy, into kinetic energy. So we can also write our power equation as U divided by delta T. And U is our elastic potential energy. So what can we write U as? We have the delta T that we see in the answer choices. But what about this K? What about this X? Just so happens that in the data booklet, we have a formula. Instead of U, it's E sub H, but it is describing the same thing. It is saying that 1/2 kx squared is equal to the elastic potential energy. Now, it doesn't say this in the data booklet, but this is only for a spring that obeys Hooke's law. Hooke's law is F is equal to negative K times X. So the restoring force is linearly proportional to displacement. This is not in the IB curriculum, but to find the potential energy stored in a system like this, we integrate the force. So integrating from 0 to x, since that would be the extension of our spring, for integrating the force, right? And then dx. Well, the force is equal to this right here. So we have this, and then that's x squared divided by 2. So yes, what we have is 1/2 kx squared. And that is what our U was equal to, right? So this formula only applies when the spring obeys Hooke's law, as it does in this question. The force might instead depend on x squared, on the square root of x, but if that was the case, we would need a different expression for f of x. So this formula no longer applies, right? Because the relationship would be nonlinear. But since it does apply, all we have to do is substitute it into our power equation. So what we have is 1/2 kx squared divided by delta t, and that simplifies to kx squared divided by 2 delta t. So that is answer choice C.